Chapter 7, slides 11 through 25. Okay, so we have looked at nucleophilic substitution second order reactions, or SN2 for short. These reactions have a lot of considerations, and if you remember, there's another type of substitution reaction called SN1 that we're going to talk about very soon. So in order for us to decide whether a reaction is going to go SN2 or SN1, we have to understand some of the things that matter when it comes to looking at a starting material and a reagent for this specific reaction. So I've listed them here. We want to consider the structure of the alkyl halide, or the alkyl halide serves as the electrophile. So we want to look at the structure of the electrophile. We want to look at the reactivity of the nucleophile. We want to consider the concentration of the nucleophile. And we want to consider solvent effects for the reaction. So let's go through this one by one. First thing we're going to do is look at the alkyl halide, or the electrophile, the carbon with the halogen off of it. Look at the relative reactivity rates down here at the bottom. When the halogen is on a carbon, a methyl, with just hydrogens around it, it is greater than 1,000 times faster than if the bromine was on a carbon with one R group, right? This is a primary carbon. It's a primary bromide. When the bromine is on a carbon with two carbons off of it, this is a secondary bromine. And when a bromine is on a carbon bearing three other alkyl groups, it is a tertiary bromine. Okay, let's think about this. Why does the reaction, so an incoming nucleophile, doesn't matter what the nucleophile is, the nucleophile is going to attack the methyl 1,000 times faster than the tertiary? What is this trend that we're observing due to? Top 3 answer in organic chemistry, right? It's actually one of those. In this case, it's due to steric hindrance. The less sterically hindered the carbon is bearing the leaving group, the easier it is for that nucleophile to kind of swing in and pop the bromine off, right? Because coming in and the leaving group leaving, that happens at the same time. So if you've got a nucleophile and it's trying to shimmy its way in there, trying to get to that backside attack to pop off the bromine, that's really tough to do. And you got all this cloud, these electron cloud density blocking your path, really, repelling you from wanting to get and squeeze into that sp3 carbon. That's hard to do. Much easier when you have an open field, right? Boom, those hydrogens are nothing. Those hydrogens really don't stop you. They're not big, bulky clouds of electron density. So the more hindered you are, primary better than secondary better than tertiary, right? Then you know that steric hindrance is going to favor, if you have lack of steric hindrance, it will favor an SN2. The tertiary bromide, not likely to undergo an SN2. Here's a question. Rank the following molecules in each one, for questions 1 and 2, rank them according to their reactivity in decreasing reactivity order, with the fastest one undergoing SN2 ranked as 1. So do this problem and see what you get. So this is helping you understand the rate. Okay, what about other aspects of the electrophile? Again, we're still on the first one. We're talking about the electrophile. What other aspects could we consider? Well, let's keep the nucleophile the same, OH minus, and let's keep the primary nature. So all of these are primary electrophiles. The only difference now is the type of leaving group. So is there a difference between the halogen of iodine versus bromine versus chlorine versus fluorine? And when you do the experiment, indeed there is. The faster reactions have iodide as the leaving group. Think about why that might be. Look at that trend. Iodine is a better leaving group than bromine, than chlorine, than fluorine. This makes sense. And we've kind of already looked at this. What pops off in the products is that leaving group. That leaving group, that negative charge left behind on that leaving group, the more stable it is, the faster the reaction. So you can think about it due to stability of atom from REO, because you're, in effect, you're evaluating a negative charge. And you can use REO to evaluate a negative charge. Thus, the leaving group trend is that the iodides are better leaving groups than bromines, are better leaving groups than chlorines, are better than fluorines. So the ones that we're going to use are iodine, bromine, and chlorine. Those are the ones that we use realistically in the lab. Fluorine is, it's almost, because it's so electronegative and not a great leaving group, it has its own uses in chemistry, and it's sort of the black sheep of the family. And so a lot of the times you'll see us doing things with iodine, bromine, and chlorine, but leaving fluorine out of it. So I won't even give you problems with fluorine. There are journals dedicated to fluorine chemistry because it has its own niche in the field. Okay, still on the topic of the structure of the alkyl halide, or the electrophile. Okay, I've got some practice here for you. The only thing changing is the halogen, so I'd like you guys to rank these from fastest to slowest, with the fastest one ranked as 1. Okay, now let's talk about the nucleophile. We've talked about the electrophile. Now I want to focus on the nucleophile and the reactivity of it. Well, as I mentioned, SN2 is a concerted reaction. Bond making, bond breaking happens at the same time, and steric hindrance can play a large role. So you have to think about not only the steric hindrance of the electrophile, but if you bulk up your nucleophile and make that sterically hindering, that's not going to work well either. So we also want to keep the steric bulk of the nucleophile on a smaller side, right, on a smaller scale. So take a look at these examples. I could have given you something like sodium ethoxide. That's simply an O- with an ethyl group off of it. That's got a slimmer profile than, say, sodium T-butoxide, which has an O- with a big T-butyl group off of it. Tert-butoxide's pretty chunky. It's a big, huge ball of electron cloud. So even if you have a small methyl type looking electrophile, or a primary electrophile, if you have too big of a base, you still have a steric hindrance problem. So you've got to make sure that the profile of both the electrophile and the nucleophile are, reasonable. Primary would be better for the electrophile, and as slim as possible, maybe methoxide, a methyl oxide, or an ethyl oxide, something smaller. You don't want anything too huge. How about the nucleophilicity of the nucleophile? How does that affect our reaction? Well, SN2 is really reliant on the strength of the nucleophile, okay? And what I mean by that is typically SN2 prefers strong nucleophiles, okay? Why? Well, because the carbon bearing the leaving group is usually just partially positive, okay? I like to call this the dating effect or the party effect. If you are a partially positive atom and you go to a party and you want to meet a partially negative atom, okay, or a negative atom, you might be attracted to the partially negative atom, okay? There's an attraction there. But without one of you being charged and bold enough, you'll never react, okay? It's much better to have an atom that has a formal negative charge because its desire is to react. It has extra electron density. It's bold enough to go and interact with that carbon. Okay, so nucleophiles for SN2 are preferred when they're stronger. So I like to see, that's not always the case, but 90+% of the times, the SN2 reaction is governed by a nucleophile that is negatively charged, like formal negative. Okay, that's why we were using something like sodium ethoxide or sodium hydroxide, right? The OH minus is formally charged. So whenever you see an ionic bond, an ionic nucleophile, you know that one of those atoms is formally negatively charged. So it's probably a strong nucleophile. Okay, so the general party trend, my party trend is that one of the pair has to be bold enough to ask the other out. Okay, so if you have a partially positive atom, it is going to actually react with a formal negative. Or if you have a formal positive atom, it will react with a partially negative. It doesn't matter which one is bolder, as long as one of them is. Partial positive and partial negative, sometimes you get a reaction, but those two go home alone, no reaction. And these are the explosive relationships. These are the ones, you know, when they tell you, don't mix those two chemicals, boom. Yeah, that's when you have formal positive and formal negative, and when those two get together, it's explosive. So these are my party effects. What you'll notice is that for SN2 chemistry, okay, we're dealing with a strong nucleophile and a partially positive carbon. How do I know I have a strong nucleophile? Well, you can look at the nucleophilicity. And as I just said, if I was comparing the same atoms, if I was comparing oxygen in one case versus oxygen in another, having a formal negative charge is a stronger nucleophile. O minus, right? This O minus is a stronger nucleophile than O partial minus. O methoxy minus is stronger than partial negative of the O methanol. The amide or the amine minus versus the neutral but partially negative nitrogen is a stronger nucleophile. So these are all better nucleophiles when they're negatively charged, right? The nitrogen versus the nitrogen. Put a negative charge on there, right? Everything on the left is absolutely negative. Everything on the right is partially negative. So when you're comparing apples to apples, the same atom, the negative, formal charge negative version of that atom is stronger in nucleophilicity than the partial charge. That kind of goes without saying. It seems kind of obvious, right? The stronger the base, the better the nucleophile. Is this statement the same for all molecules with atoms that are close in size? So let's take a look at some other cases. When you're trying to now, what I'm trying to do now is look at the nucleophilicity of atoms that are charged negative, but not the same. So I'm not looking at nitrogen minus versus nitrogen partial minus. I'm looking at nitrogen minus versus oxygen minus versus fluorine minus. And what you'll find is that the nucleophilicities or the basicities, again, doesn't matter which one, they're only defined by what they attack. What you'll find is that they're better at being the attacker or using their alone pair the less electronegative they are, right? This makes sense. We can look at it as two different ways, and I've kind of discussed this with you in the acid-base chemistry chapter already. Think about it this way. Which one of these negative charges is more stable? Going across the periodic table, nitrogen is left, then it goes oxygen, then fluorine, right? So as you go across the periodic table, REO tells me to look at the atom, N minus, O minus, F minus. F is greedier, so therefore it doesn't want to share. It's more electronegative, it's greedier, it doesn't want to share. You could also say that because fluorine is more electronegative, it's more stable. And if it's more stable, then it's less reactive. Right? So REO tells us that fluorine's more stable because the atom is more electronegative, stabilizing the negative charge. More stable means less reactive. Or you could say fluorine is more electronegative and greedier, so it doesn't want to use its electron pair. It wants to keep it to itself. It doesn't want to use it in a covalent bond. It would like to keep that lone pair as a lone pair. Nitrogen is less greedy and more willing to act as a nucleophile and share its lone pair and go and react with something. Go and react with that partially positive carbon. So when you're comparing different atoms, all charged or all not charged, as long as you're comparing apples to apples, one atom to the next, as you move across the periodic table, you can use REO for atoms. However, there is a difference, and this is so confusing. I'm so sorry this is the way it is, but it is the way it is. We don't see the same trend as we go up and down in the periodic table for atoms. Remember when we were doing basicity, okay? So in basicity, we determined that iodine was larger as an atom and more stable, thus less reactive as a base. So the trend for basicity was that as you move up, you became a better base. As you move down, iodine being larger. Remember, for the A for REO, as you move down, the atom gets bigger and you have more surface area and you have more area, and the electrons can spread out more and stabilize the negative charge. So iodine, I- is actually more stable. And we saw that actually when we were looking at trends for leaving groups, right? Iodine is more stable than bromine. So as a leaving group, iodine's the better leaving group because it's a more stable negative charge. Now what we're doing is we're not saying we're throwing off an I-. Now what we're doing is we're saying, okay, I want to react one of these and use it as a base or a nucleophile. If I'm using it as a base and just attacking an H+, going after an H+, the fluorine is more likely to attack because the iodine is far more stable due to its size and distributing that electron density. That's what we learned in the acid-base chapter. Unfortunately, this is the only divergency we see. If I was asking about nucleophilicity, if I was trying to attack a carbon partial positive now, if I was attacking a carbon partial positive, the more likely candidate is going to be the iodine. The reason here, iodine is still more stable, but there's something that takes over that's more important, and this is called polarizability. And polarizability is this, the fact that it's so big, right? The iodine is so big versus the fluorine in this pictorial, that as it's edging, right, as you're trying to come and approach this larger species, right, you're not going after a puny little tiny no electron cloud hydrogen. You're going after the back lobe of an sp3 orbital of a carbon that might have stuff in the way, some steric hindrance perhaps. So the iodine being bigger and squishier, it actually can distort. This is called polarizability. It can distort its orbitals, its electron cloud, to kind of squeeze in there a little bit and edge in and have a little bit more bonding and overlap than the tiny little tight-shelled fluorine, which doesn't have a lot of squishiness to it. So its distortion to try to squeeze in there, the nucleus is going to end up having to get much closer. The whole atom has to kind of approach much closer to even hope for the bond. So when you're actually attacking these carbon species as a nucleophile, as opposed to a hydrogen as a base, there's a difference here. The extra cloud density actually helps you, even though iodine is more stable as a negative charge than fluorine. So that's one of those weird divergencies that we see for nucleophilicity. When you're comparing it from left to right on the periodic table as above, it follows REO, but it goes against REO due to this new concept called polarizability that I'm introducing. And this is only coming in, and it really separates basicity from nucleophilicity. Okay, next, the concentration of the nucleophile. As we mentioned, this reaction is concerted, starting material, product. There's only a transition state. The rate equation for this reaction is written as K, the rate constant, times the concentration of the nucleophile times the concentration of the electrophile. So if I tripled the concentration of the nucleophile, the rate would triple. If I halved the concentration of the nucleophile, the rate would slow by half, right? So it's got a direct correlation. Lastly, I want to talk about solvent effects. Solvent effects, in order to do that, I've got to define different types of solvents. So these are solvents you're going to see throughout Orgo 1 and Orgo 2. You're going to see solvents like non-polar solvents. These are pretty much just hydrocarbon type alkane solvents. An example might be something like hexanes. 1, 2, 3, 4, 5, 6. Right? Hexanes is a solvent. You guys have used that in lab. That's a very non-polar solvent. Right? Period. Non-polar solvent. It's very limited in what it can dissolve. Then we have two types of polar solvents. We have polar protic solvents. These are things that can hydrogen bond. So, examples might be water, ethanol, methanol, right? Because it's polar. It's got an oxygen hydrogen bond that's polar. But it has hydrogens on heteroatoms, which can hydrogen bond. So it makes it a very, very, very strong polar protic solvent because it can participate in hydrogen bonding. Okay? Then you have polar aprotic solvents. Solvents that have polarity but don't have a hydrogen bonding type proton on them. So things like acetone, right? Because it's a ketone, but the hydrogens are on carbons. They're not on heteroatoms. So we've got a dipole. We've got a dipole moment there, but it doesn't have hydrogen bonding. Another example might be something like diethyl ether, right? You've got this dipole moment, but it's a polar molecule, but it doesn't have hydrogens on the oxygen, right? So polar aprotic and polar protic, those are the ones that can make or break a reaction. So how do these types of solvents affect an SN2 reaction? Well, let's remember that in an SN2 reaction, right, we have a nucleophile that's typically strong, negatively charged, and it's attracted to a partially positive carbon. So these two are trying to find one another, right? We want these two to find one another. But in order for the nucleophile molecule and the electrophile molecule to meet, I have to put it in a solvent and mix them up so that they can meet one another in solution. If I were to use a polar protic solvent, here's the problem. The nucleophile is very strong, negative. If I used a very strong polar protic solvent like water, those hydrogens, they're like the paparazzi or like the media, right? They just clamor, they're attracted. The partial positive hydrogens they're just gonna surround that nucleophile and ultimately get in the way of what it's trying to do. It's almost like it's distracting it from trying to find its target electrophile. I know this is an old movie, maybe you guys haven't seen it, but the classic 1976 Rocky movie, it just reminds me of Rocky wanting to interact with his girlfriend, Adrian, after he wins the fight. right? And he's screaming for her, but he can't get through the crowd, and she can't get through the crowd because they're just, the solvent is acting like the crowd, and they're attracted to the strong nucleophile Rocky, and they just can't get to one another. So in this case, SN2 does not want to have a polar protic solvent. Let's look at polar aprotic solvents. Here are a couple other examples. I gave you acetone and ether. Some other ones are things like DMF, dimethylformamide, or DMSO, dimethyl sulfoxide. Notice in these two molecules, very similar to acetone, there's a strong dipole moment, right? You can see the dipole, but there's no hydrogen on the oxygen or the sulfur or anything like that. So there's no hydrogen bonding. That's what makes it aprotic, not protic. Now, the trend that we see, and let me go back to the other slide here. The trend that we see is that when you have a negative charge, like a nucleophile, if it's negatively charged, it's got a lone pair it's dying to react with, right? It's just, I want to react. Typically, the nucleophiles have an octet. They're happy. I mean, they've got an octet. They just have more electron density to themselves than normal. As opposed to positive charges. When you have a positive charge, typically you're lacking electron density. And so having, others around you fills that void. Okay? We're going to talk about that a little bit more in SN1. But how can polar aprotic work for us? Well, understand that we don't buy things like OCH3 minus. I don't go to the shelf and look for, where's the OCH3 minus? It doesn't come like that. It comes as a solid salt. Maybe it's sodium methoxide. Maybe I buy lithium hydroxide, right? But the lithium is plus, the OH is minus. I don't buy OH minus. I buy lithium hydroxide or sodium hydroxide or potassium hydroxide. These ionic interactions can also detract from the nucleophile doing what it wants to do. If you've got a lithium there that I'm happy to interact with as an ionic system, because we're strongly attracted to each other, sometimes being able to carry that ion away is helpful to me so that I'm on my own. I'm a strong nucleophile on my own. I got rid of that lithium or that sodium. Sometimes to enhance the reactivity of a reaction, we can use polar aprotic solvents because what they can do is that their negative end can surround and carry away the positive counter ion, stripping the nucleophile of its counter ion and allowing that nucleophile to go and do what it needs to do. So typically what we see is that positive charges have good effects with solvents. They're helpful. You can see this in biology a lot. When you think about potassium and like sodium pumps and potassium pumps and transfers across cell walls, cell membranes, these are carried by molecules. And we often can see these types of carrying through with something similar to this. These are called crown ethers, and we can use them to trap various sized atoms. So if I wanted to pull away this lithium counter ion, I might want to use a smaller 12 crown 4. This is a cage that it's built. Those oxygens are partially negative of the ethers and they trap, and it's a perfect size for a small lithium ion. It's like a little cage built just for the lithium. If I wanted to trap sodium, sodium is slightly bigger, and so I'd need to trap it in a 15 crown 5. It's a slightly bigger cage, and all those oxygens are attracted to that sodium, keeping it in its cage. And if I wanted to transfer a potassium, which is even bigger, I'd have to use an 18 crown 6. you guys might see these cryptans in biology. They're basically just cages for counterions, and they keep them and then they encase them in this very organic sort of molecule to help transport. So stripping the counterion to release the nucleophile out to do what it wants to do is also helpful, and polar aprotic solvents can do that. Polar protic solvents do a little too much crowding. They get very attracted to the nucleophile and stop the nucleophile from finding its desired target. So now I've got some substitution reactions, SN2 substitution reactions for you to try on your own, okay? For each one of these, you want to circle the reaction that will happen faster. In the next set, I want you to provide the mechanism and resulting major product for each of the SN2 reactions. So notice I'm telling you here, these are SN2 reactions. I want to end with this slide, which is something that I'd like for you guys to print out and have next to you, just like a periodic table. This is sort of a cheat sheet summary of the mechanistic motifs I want you to learn. Remember, I said learning organic chemistry can either feel like a massively daunting task of memorization, and you'll feel like you have to memorize every permutation, or you can learn the mechanism motifs for each of these types of reactions, figure out when to apply them, and then, just like math, understand that I know how to do addition. You can give me any number you want. I know I can add those two together and give you the product. I want you to be able to use these just like you understand functions in math. So far, we have covered acid-base chemistry, right? We've looked at acid-base chemistry, and that was in chapter 3. We've also, in chapter 6, covered the radical halogenation of an alkane. That's recognizable in this rad or radical reaction. And we have just finished covering SN2 reactions. We're next going to cover SN1.